So in the last part of these lectures, I will talk about trajectories and how you can measure trajectories in quantum systems with weak measurements. So of course, in principle, there are no trajectories in quantum mechanics, but there are many ways to define trajectories. So as you know, Feynman propagator is a sum of the paths. And in particular, in the semiclassical limit, when h bar tends to 0, then the semiclassical propagator is a sum over classical paths. And this holds for many systems. So I will see how we can try to see the path of the semiclassical propagator. So I will introduce a little bit what this is, because I guess most of you are not familiar with that. And also, there are well-defined trajectories in the Broglie-Bohm model of quantum mechanics, which is based on the existence of a particle following well-defined trajectories guided by, so those trajectories are due to the fact that the particle is guided by a pilot wave. And also weak measurements are related to the velocity field of the Bohemian trajectories. So I will also introduce, I don't know if all of you are familiar with Bohemian mechanics or the Bohemian model, so I will introduce a little bit the Broglie-Bohm's model. So I will use interchangeably the Broglie-Bohm or just Bohemian. And we will see how we get reconstruct the velocity field and then compare both approaches, because the semiclassical propagator gives you trajectories that are very different from the ones predicted by the Bohemian model. So I will try to do things quickly and just give the minimum I can give so that you understand what is going on, because otherwise, of course, it would be pointless. So this is the evolution operator when you go from 1 to 2, so from point x1 at time t1 to point x2 at time t2 in so the evolution operator in the path integral form. This is something that you probably came across. And the interesting feature is that, of course, here you have the Lagrangian, so time integral of Lagrangian, which is a classical action. And what I'm looking at is what happens to the propagator when the classical action is larger than h bar. So this is very standard. If you take any path integral text, you will find this. So we're taking the asymptotic limit when this goes to 0. And then K is denoted, the propagator is denoted semiclassical propagator. And it's this thing, which is sum over paths that can be any type of path each with this type of amplitude, well, becomes a very well-defined sum over classical trajectories linking point x1 and point x2. This is just the classical action then. And this is also, at least when this is squared, this is also a classical quantity, which is actually the classical amplitude. So each trajectory has a classical amplitude, which gives you an idea of how two neighboring trajectories diverge when you leave from one point. So then, once you get this semiclassical propagator, you can do several things with that. So the important thing is that since this tells you that your quantum system will evolve along classical trajectories, you somehow expect to see those trajectories in the quantum systems for which this approximation holds, right? Because this means that we have K equals KSC plus some asymptotic expansion in h bar. So if this approximation holds, and in the corresponding quantum systems, you expect to see the traces of these classical trajectories. And the same happens with the wave function at some given energy, simply because if you take the Fourier transform of this propagator, again, the asymptotic expansion, then you get a level density function. So that is simply a function that peaks each time you have an eigenvalue of the Hamiltonian. And this trace formula tells you how this level density function can be constructed in terms of the classical periodic orbits that exist at the given energy. So this also means that if you look at your eigenstate of the Hamiltonian, at the wave function, you expect to see the traces of these classical trajectories. So just to give you an illustration, then I will go to the Wiki measurement part. This is one of the systems that had been studied. So all these things were introduced in the 1970s and looked to in the 1980s, 1990s. This was one of the most widely investigated systems, which is a hydrogen atom in a magnetic field. So you can solve the Schrodinger equation, of course, but I will just, in this slide, it will just be the classical Hamiltonian for a classical electron in a repulsive Coulomb potential, so a hydrogen atom treated classically. So if you adjust B and the energy so that you get regular trajectories, so you can go near the nucleus here, then you launch your electron. This is the trajectory you will get, and if you wait long enough, this is the type of trajectories that will obtain. Now, if you adjust B so that the regime is chaotic, an initial electron launched here from the nucleus will have this type of motion, and if you wait long enough, it will just fill out the energy shell. This is purely classical. I'm just doing classical mechanics. Now, I can solve the Schrodinger equation, so I have this. This is becomes a non-separable two-dimensional Schrodinger equation. I have to solve it numerically. There are no analytic solutions. But if you do this, then you will see that if you have the same magnetic field and energy parameters as in the classical case, this is what a typical wave function would look like. And if you change the parameters so that you're in the, so that the corresponding classical system is in the chaotic case, in the chaotic regime, then this is what a typical wave function will look like. So as you see, the correspondence is even visually visible. So it's pretty, this shows that the trajectories of the semiclassical propagator are very relevant to describe these quantum systems. So what has been shown, so I don't know if I need this actually here, but so that there is a correspondence between the quantum properties and those properties of the classical corresponding system. This can be seen in the energy level statistic, the wave function, which is saw an example. You have quantum signatures in other variables also. Entanglement dynamics is also pretty much correlated with the underlying classical dynamics. And all this has been experimentally observed, but what you observe are just the manifestations. Of course, you don't, so you can, when you compute the wave functions, you kind of see the trajectories, but when you do experiments, you don't see the trajectories, but you see the manifestations. So this is an example, again, for the H atom in the magnetic field. So this is a recurrent spectrum, what is called a recurrent spectrum. So basically, you launch a trajectory. So this time you don't launch a trajectory, you just excite the hydrogen atom with a laser. And then you shine a second laser at different times to monitor the waves, the wave function that returns to the nucleus. And then you detect this. And basically, what people saw is that the recurrent spectrum they only saw peaks at discrete times. And they realized that these peaks corresponded to the periods of the classical orbits. So in this sense, we don't see the trajectories, but we see the consequence of the wave function propagating along the trajectories, because we just have peaks at some well-defined times. They correspond to the times of the orbits that I drew here, which are classical. And the amplitude, so the height of these peaks, is simply correlated, is proportional to the amplitude of the classical orbit. So this again means that the trajectories of your propagator drive the dynamics, and even though you don't see the trajectories, you see their effect, right? So this is, so this is an experiment. Well, so this is the same thing I just showed you here, but an experimental realization. So this is
So basically what they do here is they obtain a spectrum by scanning the energy, then they take the Fourier transform of the spectrum, and then this plays the role of time. This is just to show you that they really see all the evolution of the classical trajectories as the energy has changed. So they do this for every energy, and then they see discrete peaks. And this is really experimental. So this is just to tell you that the manifestation of the orbits are seen experimentally, but you don't see the trajectories themselves. So basically what we would like to do is see if with which measurements we can see these trajectories. So that would be the aim here. So what we try to do is, well, we know that a trajectory will be defined by the position at some given time. And of course, ideally, we would like to have the time interval go to 0, so you have a continuous, you can monitor continuously. In practice, we will just assume we have weakly interacting pointers placed on the grid. So we start from an initial quantum state that is well localized in position. We assume that this system is well described, at least for short times, by a semiclassical propagator. I'm just writing the same one, you don't see it, but it's the same to propagator. And then what I will do, I will post-select at some given position. So if you want, so I start from here, and then I will post-select somewhere, I don't know, here, for example. And what I can do is just have a grid of weak pointers. So the weak pointers are on the grid. And as we did this morning, we assume that each pointer is coupled locally to the spatial wave function, the small g here, which is the effective constant, coupling constant. And so what we're monitoring here is the position of the electron, if I'm launching an electron, when it hits the weak pointer. So basically, then we will read the weak pointer's state. And we know that the weak pointer state will be changed proportionally to the weak value. And so if the electron went by this system, whatever, the particle went by the weak pointer, then we would expect to see a change in the weak pointer state. So this is the idea. So what I just said, so the quantum pointer will fire, so of course in a weak sense. When? So we start from this initial state, which is localized at some point. This is the evolution operator. We just said that the evolution operator is semiclassical propagator. So basically, it will evolve along the classical trajectories that can reach point F, RF. It can be more than one. That depends on what you do exactly, on how you control your initial system. So if you are able to launch only a specific set of trajectories, which is what I will be assuming, then you will own only the pointers that will hit this trajectory will fire. Right? So this is a semiclassical propagator. If I can choose I can choose a Gaussian pointing in some direction. For example, I can choose a Gaussian that will just move along this direction. I just take the mean momentum to be along this. And then I will only obtain a Gaussian evolving along this trajectory, if there is such a trajectory, essentially. Of course, you can have many trajectories. The important thing here is post-selection, right? You're only interested, there are many trajectories that can get out of the initial state, but you're only interested in the ones that will reach the final point. Well, that will depend on your system. Of course, I will choose a model system that mimics a semiclassical propagator in which there's only 1, 2, or 3 trajectories. So that, of course, you can choose the system, you can choose the dynamical regime so that you can actually make sense of what you see. Because, of course, if you have many trajectories that can, reach the same point, which is not the case for an arbitrary system anyway, then all the pointers will fire and you won't see anything. Except that in principle, you can also post-select the position and a backward directed momentum. So you could do that also. This would, of course, help you in throwing away most of the trajectories. So if we look again at the weak value, initial state, semiclassical propagator, so then it means that, so if I assume all these trajectories can exist from the initial state, so this means that the wave evolves along all these trajectories, right? That's what the semiclassical propagator means. Then this is where we make the weak measurement, the projection at point R. So I will just look at, we'll just look at this one. And then what do I have? I have this term. So I have the final post-select, the final point where I will make the post-selection, a position measurement here at RF. And I go backward in time. So actually here, of course, since I haven't chosen anything, we can go backward in time along any trajectory that leaves RF. But actually, you want to go backward in time. The only trajectories that will give me non-zero are those that link, for which a classical trajectory, because this is again a classical propagator, links RF and R, so it links the position of the pointer and the weak quantum pointer and of the final position, the post-selection position. So basically, I will just show an example where this is not verified by. In general, if you want to link, so here we have evolved forward in time. This is point R. And now I'm looking at the trajectories that start from here and evolve backward in time up to, this is R, up to here. Right? So this, of course, this one will work. In general, it will be the only one. You could have systems for which you may have a second trajectory that also that's perfectly possible. But in typical cases, this means that the condition to have a pointer that fires is that the backward evolving and the forward trajectory and the forward evolving trajectory are the same. So basically, since you post-select here, the only trajectory that will lead to pointers that will see their state change is this one. So basically, this tells you that if you post-select here, and if you have a sufficient number of pointers, then you kind of see the trajectory. You can kind of infer the trajectory by just looking at the pointers, right? So we'll try to, so this is a model system, which is a time-dependent harmonic oscillator, which is very nice for simulating a very simple semiclassical propagator, because you can choose which trajectories you launch, and you control how the initial Gaussian changes or not changes. And this just is ruled by the time dependence of the oscillator.
So I start here. You see, I have three trajectories because I chose to launch a wave function on three trajectories. Trajectory 1, trajectory 2, trajectory 3 that you see here, and this is how they will evolve at time tf. This is what basically the center of each Gaussian follows the motion of the three classical trajectories that you see. And this is where they land at time tf. And this is, at that time, I will choose a post-selection. So, of course, you can guess that if at tf I choose a post-selection here, then I will never have a successive post-selection because there's no wave function at time tf here, for example. At time tf, I can only post-select successfully here, here, or here. So, basically, this is just an illustration of what I just showed you here. If we post-select at A, which is on this black trajectory, then the only, so I don't know if you see this little these little boxes here are the quantum pointers, and when they're shaded in blue, it means they have fired. And when they're left, I'm not even drawing most of them, in white, it means they don't fire. So only the trajectories along the little, only the pointers along this black trajectory, the blue here, fire. Right? And so if you post-select at B on this trajectory, then basically it's only the blue trajectory that is revealed by the weakly interacting quantum pointers. So again, it's, as we are now used to this way of thinking, it's forward propagation of the initial state up to the point where you have your weakly interacting quantum pointer, and then backward propagation from the final position that you select up to whatever you want, but it will only give you non-zero if this is not zero. And this works if you are on the classical trajectory. So in principle, if we don't know the dynamics of a system of this type, okay, in which you have let's say a very low number of trajectories with high amplitude and which remain localized for a pretty long extent, then you can, by just making weak measurements, reconstruct the trajectories of the semiclassical propagator. That's what you do. So here I show you a case in which you can have a single pointer that fires. So that happens. So here we put select at B. And it turns out that before reaching B, you have another trajectory another trajectory that links B to this point M that is on the black trajectory and not on the one on which you are post-selecting. So you can have that type of accidents in some sense, but you can discard this. Well, it's not an accident. This is allowed by the dynamics, and it's okay. But still, you understand why. And of course, if you post-select here, then in principle, the pointers along all the trajectories that reach this final point at the given time will fire. And so since I've chosen this at this time here, so all the trajectories come back to the initial point. And so all the pointers will fire. That's what this tells you, and this is just an application of the sum over paths of the superposition and weak measurements, just as we saw in the simpler example involving the interferometer we saw earlier this morning, in which you could have both pointers on each of the arms fire. Then here you have all the trajectories that can be reconstructed because these are compatible with your final post-selection point. Okay, so this is how, with weak measurements, you can try to
well, no, you actually, with weak measurements, you can define weak trajectories by looking at the position, a sequence of positions which defines a trajectory. Now I'm going to do something different. I'm going to jump to the Broglie-Bohm model. So I don't know if I should describe, I mean, who is not familiar at all with the Bohemian model here? You please raise your hand if you're not familiar at all. So I will explain it a little bit. Basically, what you do is you start from the standard wave function, and you do a polar decomposition of the Schrodinger. You feed that into the Schrodinger equation, and what you want to obtain is a guiding equation, because, okay, so the Bohemian model, you have the ontology is that you have point particles and waves. The point particles describe well-defined trajectories, and the waves are the things that guide the Bohemian particle. So by doing this polar decomposition and then feeding this into the Schrodinger equation, you can define a guiding equation. And so this would be the velocity. So this depends on the wave functions. For each specific wave function, you have a different velocity. And of course, you have the equation of motion in a Newtonian-like form. So if you integrate this, you can see the Bohemian trajectories. So the main difference between which is a huge difference, between what you get here and the standard Hamilton-Jacobi function is that you have an external term, which is sometimes called quantum potential. And this is what gives you a very, very different behavior than what you could expect for classical particles, well, at least for classical dynamics. And this will crucially depend on the wave function. Okay, so this is a very nice picture of Broglie by one of the well-known photographers of the second half of the 20th century, which is Welge. And since I'm in the sequence of pictures, this is a picture of Aronoff when he was a bit younger. Exactly the same. Okay, so this is the double-slit experiment. Those are the trajectories that were computed for Bohemian trajectory. The Bohemian trajectory is computed for the double slit. So the idea is that you recover the interference pictures because the Bohemian trajectories, they just follow the current density that you can compute directly from the Schrodinger equation. So that directly drives you to the final point, which will be on the screen here. And of course, there are no trajectories where you have no trajectories landing in the spots where you have a vanishing interference. That's it's built in, so that works. So now, what is the connection with weak measurements? So here I'm just repeating the same thing and using a different notation, which is not very wise, but okay. So if you remember that this is the Schrodinger, the current density associated with the Schrodinger equation, then as you could do for any hydrodynamic field formulation, then you can just put the standard Schrodinger current density as equal to the density, which you get from here, times the Bohemian velocity, which is here, right? So, if we now take the weak value of the momentum operator pre-selected the wave function at time t, psi t, this is the wave function, and post-selected at the position RF. I don't know if I do the computation. So maybe we should do the computation. So basically you get the real part of this weak value is basically the Bohemian velocity. And then of
course, we've got the imaginary part, which is something else. So this tells that by doing weak measurements of the momentum, we can actually experimentally determine the Bohemian velocity. So I don't know why this is here. Okay, I don't know if we will do this. Well, at the end, maybe if you want. And so this has been done experimentally by Steinberg and collaborators for photons. So basically what they did, so this is not the, I have a problem with the presentation. I think this is not the correct file. I wanted to show you how he actually obtained this. I think I will explain it because otherwise I will have to take the. So what he did was to couple, so we have the photons. A certain motion, a certain momentum. And then, so he couples the transverse momentum to the polarization. The polarization state acts as the pointer, and that allows him to retrieve the momentum. So I will write that down. Just take the notes, because I think it's very instructive. Sorry for the glitch. Yeah, so actually I don't think we can connect the machine. Wait 1 second, I'm sorry. So I don't have it here either. So I'll try to explain. I'm sorry, I think there's a cloud issue. I think the file got erased by some file that was on the cloud. This could explain. Sorry about that. So basically what he does is uses a crystal and couples the polarization to the transfer part of the momentum. So we have a certain polarization state. So this couples, so this is the wave function. This couples, plays the role of the pointer state. So you see, you don't have the Gaussian as we have seen earlier today, but we have a polarization state. Then, so there's coupling here that depends on the thickness of the crystal, because this is done by a crystal. And when you do assume that this is small, and finally you will select at some point RF, well, XF here, because I'm only looking at transverse momentum. And when he does this, then he reads the change in polarization that is produced by this interaction, and this allows him to retrieve Kx weak. So you do the usual asymptotic expression we have done, and then this allows him to retrieve Px weak, which is so what this is done for each position, right? So he has to do this for each position x, xf. And after he does this type of thing many times. So for each transverse position, this has to be repeated several times, and then he moves the position xs, and at the end he reconstructs, that allows them to reconstruct all these velocity field that is obtained at each point. And from the velocity field, you reconstruct the trajectories that are consistent with this velocity field. So this was summarizes what I just said. So the important thing is that the pointer is played by the spin, which is actually the polarization here. And by reading the polarization, the change in this initial state reveals the weak value, the real part of the weak value of Px, which is just the Bohemian velocity. So, the thing is that I'm afraid I cannot show you I don't have the pictures. Mm-hmm. Because now so if we made weak measurements of the position, sequential weak measurements of the position, we saw that we could get classical trajectories. And if we make weak measurements of the momentum, we have a velocity field, which is consistent with Bohemian trajectories. No, no. Okay, so this is what I was aiming to. So basically, we're testing the dynamics here, right? Because we are not seeing a Bohemian trajectory nor a Bohemian particle. We have a photon, and actually we stop for each XF. We just put some screen if you want, some camera, and we have a
have a point here which tells me that the photon was here. Yeah, I will forget the issue about the photon wave function. I will just assume that this issue does not arise. There's, of course, a problem with the photon wave function. Why? No, I'm just saying that actually what is done by this experiment is measure the weak value of the momentum. The value of the momentum turns out to be also the Bohmian velocity. But that does not mean that there are particles following Bohmian trajectory. This is a reconstruction. This is what I want to emphasize. And the reason, the point I want to make here is that if you make a sequential, so for example, let's even take a simple case. Well, I'm interested in this type of thing. So if I look at if I select here at this position and I look at the weak trajectories, well, the weak trajectories, okay, I have many pointers here and I have pointers here. So the only the pointers that will fire are the orange one, and those are post selection here. So only these weak pointers will fire, right? So this will be the weak trajectory in this very simple case. Now, if you want to compute the velocity field everywhere, so I'm just throwing arrows. So this here is very obvious, but as you know, I will kind of emphasize here. When you reach the crossing point here, the velocity field, the transverse velocity field here vanishes. And this means that your Bohmian trajectories go like this. So the Bohmian trajectory that was detected here, according to Bohmian mechanics, goes this way, right? There seems to be, I mean, if you think that this experiment shows you that Bohmian mechanics is right, then there seems to be a problem in accounting for the fact that the post-selected particle here only sees the weak pointers change along this trajectory. Now, if you make weak measurements of the momentum and not of the position, then you will have a velocity field like this. And if you reconstruct trajectories from the mean velocity field, then you will see, of course, since here it goes to 0, you will see the trajectories go this way. No, you cannot conclude that it is wrong. Once you accept that there are non-local interactions and that the Bohmian trajectory that is here is able to produce an effect here, if you accept this, then it's not wrong. Maybe it's not very plausible, but maybe it's like that. Maybe nature is like that. But at any rate, you cannot conclude from the weak measurement of the momentum operator that Bohmian mechanics is right. You just make a measurement of the current density, Schrodinger current density. Yeah, so actually, I don't want to get into this discussions. Of course, the wave function of the photon is a very strange object which has special properties you cannot localize. Yeah, but here actually the Bohemian interpretation for photons would, I mean, it would break down. So we should assume it turns out that it's very, very difficult to do weak measurements, and that this has been done for photons, and only do something different, it's extremely difficult. And so this is why the experiment was done with photons, but let's just assume this is a massive particle. Otherwise, I don't think we could include anything else, that this is the way the energy flows, the Poynting vector. It's reproducible. It's I'm not sure according to the Bohemian model, or what happens to the photon. Me, how I would so I'm sure I understand the question. This figure I would explain by saying that we're just looking at the Poynting vector, the energy flow of the electromagnetic field. I don't understand in between, because this is, you understand that this is done for each transfer position, right? And then another experiment is repeated and so on, okay? So then we only detect one photon. So at each time, okay, they record some photon, because this is a thing. So this is a single photon experiment, so they do this one by one, and they do this thousands of times, and they get this figure, yes. So actually the screen moves. Each time they do the experiment, the camera moves. You mean this? Yes. I don't think I understand the question, because wait, the photon path we don't know exactly what it does, right? So we have to make some type of measurement and then make some interpretation. So according to, so if I have the two slits, this is what I try to, this is the measurement of, if it's not a photon, if it's a massive particle, there is no doubt this is the velocity field, or if you want, the current density associated with the Schrodinger equation. So at each point, so if you want, so we start here, we send one photon, we have thing here, right? And then this is associated with, he measures the position and the weak value of the momentum like this. Then we reconstruct, we do another experiment, and here we find something, here we find something, and so on, and then he moves the screen and does another experiment, and now he will find something like this, and so, okay, so this is what he does. And so this gives you the mean velocity, and so you can just draw a line joining all these velocities, and this would just be the current density associated with the Schrodinger equation, period. But that doesn't mean a single photon does this. This is, that is, I think, where there's a confusion. This doesn't show that a single photon moves according to this. So at each point, we make a weak velocity, weak momentum measurement, and then we just draw a line, but there's no way to prove that a photon did this. Yes? It's built in, because the current density will drive the yes. It will be zero where you have yeah. Again, this is not a trajectory. This is, you don't know that a photon took this trajectory. Unless you believe in the Bohemian model. If you believe in the Bohemian model, then you will say that in reality, there is only one photon. The wave goes through both slits, but the photon goes either like this, and in some other experiment it will go like this, and some other experiment it will go like this, and so on. So if you like the Bohemian model, then this is something you can say. So this shows you that you can measure the current density by, in general, they say that this is not a measurable quantity, it's not an observable, whatever. This is what we usually learn in textbook. Well, they did a measurement, yes, with weak. Well, it depends on your point of view, because the people who did this experiment wanted really to show that they have arguments that indicate that the Bohemian model could be, let's say, real. So that's the motivation, and of course, it can be the case if you abide by a certain assumptions they make, but we don't have to take this assumption at face value, we can make other assumptions. So what is undisputable is the results they obtain. I mean, they just measure a velocity field, which is associated with the current density. This is undisputable. Now, how to interpret this will depend on several assumptions we want to make, and the first of all is whether a quantum system is decomposed as a particle plus a wave. So if you don't make this assumption, you can't even talk of trajectory. So this is really no. I think you remember that they always tell you that J is cannot be measured. It's not an observable. So strong measurements, you need to have both R and P, and so you cannot do it. With weak measurements, you can do it because you measure P and post-select at S. Yes, and you can do this for any type. You can take two non-commuting observables, and you can measure them jointly. Something you can do with one of them measured in the week. Yes. That was the question we were discussing. So the answer is no. Not an experimental proof, but if you like the Bohemian model, then you will like this experiment. This is basically the conclusion. So I just wanted to emphasize that it is just, so we won't do the tutorial because this was not what I had to do. Yes, because the Bohemian velocity is just proportional to the current density. So if you measure the current density, you measure the Bohmian velocity. So, and if you measure the weak value of the momentum, then you measure both the Bohmian velocity and the current density. But you see, since the people who support the Bohmian interpretation, they have always been told that their trajectories are in principle not measurable, and so it's just a fiction, and so they can, just go away. They are happy that this type of experiment is compatible, let's say, really compatible with the interpretation. But it doesn't prove it. I mean, if you don't, So we won't do this anyway. But there is, we can actually prove that we can prove that this weak, so it's here actually, so that this weak value is equal to the limit of the weak value of the position defined here. So you have your wave function at time t. Then you have the position operator, and this is a very small evolution that you want to make as small as possible before you go select just right away. And so, well, you didn't seem to be very shocked, but of course, I mean, you have two ways of defining trajectories. One, which is by making position measurements, which gives you one type of trajectory, the one that is actually compatible with the classical trajectories of the semiclassical propagator, and the other one, which is by looking at the velocity field and then reconstructing a trajectory. From the velocity field. And so, well, it's not only a surprise that you can get this velocity by making, looking at this two successive measurements, one weak and one strong, which are done in a very small time scale, short time scale. So this is something that can be proved. So what I just wanted to note is that there's no contradiction between the mean velocity, the current density, and the trajectories we get here by looking and making subsequent measurements, because actually what you do here is you do a weak measurement at point R, then the system evolves in an extremely short time, and here you make the post-selection at point RF. And of course, the wave function is actually, in general, at some extent that is larger than the distance between these 2 points. And so this explains that actually when you take this formulation, when you have two waves that interfere here, the current density will actually see the result of the interference, because it will have the wave function that will evolve in this time. One will evolve like this, so that's the one going upwards, and the other will just evolve like this. And so when you just compute the current density, even though, again, the weak trajectory going here will, the weak trajectory compatible with post-selection here will go this way, and the other is supposed to go that way, the current density here will be 0. So this is something that comes out nicely if you write the weak value of the momentum in this way. So actually, since I think I'm missing pictures I wanted to show you. So I don't know. I will just quickly mention some other applications. So here we have essentially discussed, which was what I wanted to emphasize, the applications, the foundational issues where you could apply weak measurements. So you have some practical applications. So one of them is parameter estimation. So basically, you have a small parameter you don't know, and you want to know what it is. And since it's small, it's not easy because you usually have background noise and kind of thing. And so if your resource is cheap, then you can use weak values for that. So the idea is you have a reference situation in which you have an initial state, and then this goes into a final state in which you make a strong measurement, and it has some probability. And then you do something that perturbs this initial state. So this, typically, this has been applied, for example, if you have a beam, then a crystal here, very fringent crystal, then you will have a small displacement of the beam as a function of the polarization, and then here you will make a final detection. And so what you want to know is what characterizes the crystal, which is the parameter you want to estimate, and this is actually, you can read this in the displacement you see in the position-dependent displacement you see in the beam. So, so if you have a Gaussian beam, then you would have, this would characterize the interaction between the crystal and the beam. So this is again the polarization which I wrote earlier. And so this would be the detection probability, assuming epsilon is small. Then you will do detection here, so you post select on the polarization, and then at some position x, you will you'll find the beam. So in principle, you integrate over all the x points. So I didn't do this here, but basically it's just to show you how it can work. Is that since the perturbed, so the probability is of course proportional to what your intensity of the beam will measure. And then from this thing, you can retrieve epsilon, and this depends on the weak value of your polarization operator. And so if this is small, then you can amplify and find epsilon. So the caveat is that when this is small, I don't know if you remember, but this also means that the probability, if the weak value is so this has been done in a lot of works, and so I think the first one was this work by Hostin and Quiet, in which they looked at the displacement for photons passing through an air glass interface. And in general, you can do this to measure small deflections. So here it's produced by a crystal, it can be produced by anything, like frequency shifts, temperature shifts, and whatever.
whatever, and this has been employed. And of course, again, this is useful if you can make a lot of funds. Otherwise, it's not very useful. So another application is when you can measure complex weak value was the direct measurement of the photon wave function. So again, you have several experiments. And so the idea is to measure this weak value. So make a weak position, so it's actually it's quite the opposite of this. You make a weak position measurement followed by a post-selection on the momentum. And if you just compute this, you will have a term that is you have a term which is proportional to the wave function. So just as we saw, we could measure here the current density, the position, and the momentum. This you can apply to any pairs of non-commuting operators. And this has been applied to try to understand the measurement precision disturbance relationship. So this has been debated in the last few years. So this could take too much time to get into it, but in principle, if you want to measure the disturbance, you should be able to measure the value before and after the point has interacted with it. And this is, of course, impossible in principle in quantum mechanics, but if you make quick measurements, then you can do it. That is the idea, and that has been used also in several papers. So, yeah, so I think I will stop here because I wanted to show you some pictures, but they don't have them with me, so I'm sorry for that. If you have any questions. Yes. So it's, unfortunately, there is no review paper I could recommend because there are no review papers in this field. Original, yes, so but it's very limited compared to what. So the original paper is the yes, the one. Let's see the paper in which the weak value was introduced, and of course this comes from the 1960s with the ABL rule and contextuality, that kind of thing. So, yes. So that's correct in theory. So as you saw most experiments here, they use, for example, the experiment by trajectories, the Steinberg here, they use another degree of freedom of the system as a pointer, right? So you're making the weak measurement spin is the same component as the strong measurement spin? Or because... Well, okay, but which spin you're talking about? Okay, you have In the z direction, for example, you have plus z? Okay. And what is the weak measurement? This, but what are you coupling? What observable are you coupling to the pointer? Spin in the z direction, okay. So actually you have some plus alpha, this is what you have, and you measure in sigma z. This can always be written as a, so this is minus, this is plus, and so this I should not call alpha, I should call, I don't know, that's cos alpha divided by 2 plus. Yes. Yes. Okay, yes. Basically, you have this would be the original one, and then you would have this one and that one. So strong measurement, sorry, I just need to know strong measurement in which basis? So if you make, so no, because here you're making the weak measurements in the Z basis, and then the strong measurement you also want to make it the Z basis. So then weak measurements are, yes, in this case it's adding nothing, because actually, I mean, these two guys compute because they're the same, so you're not doing anything by doing the weak measurement in this case. You're just doing the strong measurement, and this thing doesn't add anything. So this is interesting when these two don't commute, right? So if you take something different, that's where, so basically the weak value becomes an eigenvalue when you do this. So there's nothing, this is why some people say that the weak value is a generalization of the eigenvalue in the sense that the eigenvalue is a subset of the weak values you can obtain. The post-selection is an eigenstate of the weakly measured observable, which is the case in what you said. Yes. No, experimental one. It should be the same. I'm not sure here they were able to measure sufficient trajectories to infer something about the entity. So here you essentially want to look at the velocity field, so I don't know if this is an indicator of the entity, because then we probably need more measurements than they did. So I don't know, I don't think this is, probably not, and this would be more, this is a computation, so this would be more relevant to discuss entity. Where you see a lot of black, we have many trajectories that are very nearby, and where they are separated, and when you don't have anything, then it means we'll have an interference, vanishing interference. But in the experiment, I don't think they did sufficient. It's impossible. No, it's the same thing, except that here you just compute as many trajectories as you want, and so you have all of them in some sense. Well, you can compute more, but and here you only have a subset of the trajectory.
Yeah, no, this is a mistake. This should be coming out from this list. Yes, this was added with something different. Okay. Any more questions? Yes. No, that's it's due to this term. So this term tells you that when there is an interference, as you see, if there's a vanishing interference, then R goes to 0. This goes to infinity, so it becomes huge. And so if you have it's called a nodal point, in the trajectory that comes here, it will avoid the nodal point. So this is where it comes from, and it's really, so this is a really, a real effect that is in, this is actually how the Bohemian trajectories take into account interference, by avoiding the nodal points. Okay, so yes. Which problem? Yes. The answer comes. So maybe I said, so actually, PA has two subspaces. It's A and B plus C. Right, so this is associated with eigenvalue 1. So, so if you compute the probability of obtaining -1, which is PA bar, and
Actually, what I want to check that this is a projector, so maybe we can do this together just after two, not to have everybody waiting. So we can work on this just after one. Because if there's no more questions, we can finish. Are there any other questions? Okay, so then, thank you very much. Okay, so let's. No.